Nijil, you're an international student, are you?
Yes.
From where?
From India.
India. And you plan to go to higher ed once you finish this diploma?
Yes. I'm planning for electrical engineering.
Electrical engineering. Oh, yeah. They'll be lucky to have you.
Thank you.
Okay, we wait for a couple of minutes and plenty of problems to start. And what about you? What discipline you want to do?
I'm doing software engineering.
Software engineering. Oh, that's good. And have you done any programming before?
No.
Yes. So
Will it be hard if I'm not familiar with that?
yeah, there is something called algorithm.
Yeah.
If you're familiar with algorithm, that is the systematic thinking of the how programs work.
Yeah.
Loops, repeat, movement of the command or something like that. And then few languages, computer languages, are more useful than the others. I mean, in my time, I did for computing, Fortran was very good, and C language was good. I chose Fortran, but Fortran these days is not used as such. But C++ is something you want to do, and there is a web page. It's a free. It has all the programming languages in it, and then that has a screen. You go program here, and the next screen you see the execution of the program.
Yeah.
If that's HTML, you write the code here. You see the HTML executed over here. C++ the same. So yeah, these are very useful, and I think that's one of the disciplines on demand.
Yeah.
If you are a software engineer and you can do programming, that's the toughest thing for automation. So even in robotics, people do all these sensor actuator selections, but when it comes to programming, that's a very specialized thing that only software engineers can do, and that's a good thing. Yeah, bright future. Okay, good morning, everyone. Today we have um, demonstration session. So I would start the session by jumping into page 125.
Good one.
Good morning, come in, come in. Where were you yesterday?
Fantastic.
Okay, make sure you watch
Yeah.
the
I
recording.
was happy.
Okay, 125 and then 124. All right, this is a plate and the coordinate system has been selected in figure. we want to find out the moment of the forces acting about x, y, z axis. Okay. So how this can be done? I mean, one by one. The moment of 200 Newton, what axis would be the rotational axis? That would be about y, right? Okay. It won't make any moment about z. It won't make any moment about x. Why? Because it is parallel to z, and therefore it cannot make a rotation. And also it is colliding with x, so therefore it doesn't make any rotation with x-axis, but with respect to the y, it does. If you want to do a scalar calculation, how do you do it? That is the magnitude of the force multiplied by the shortest distance between 200 and the y-axis. What is the shortest distance there? So that's 2. Between 200, I'm talking about this 200 here, with respect to the y-axis. So that makes this rotate, and then that goes through a circular motion, doesn't it? It goes like a circular motion like this, and the radius of that would be 2 meters. That's the shortest distance. Okay, so the moment due to 200 is is this positive y or negative y? Just take your four fingers to follow the direction of rotation, and your thumb would be opposite to the y direction. So if I want to write that in vector, don't worry, I explain. So this is the magnitude. Magnitude is 200, and the radius is 2 meters. And that makes, just use your right hand, 4 fingers are following the direction of the rotation. 200 with respect to the y, your thumb would be opposite to the y. So that is minus j.
So it's anti-clockwise, right?
Don't worry about clockwise, counterclockwise is only when you want to add the scalars. So you don't know how to add the scalars. Clockwise, counterclockwise help you to classify them, and this is a convention. But this is about the vectors. Vectors are with the unit vector, and we are using the right hand rule. And let's see what 50 Newton does. The moment of 50 Newton, does it make any rotation about x? It colliding with x, it doesn't. With y, colliding with y doesn't. Colliding with z. So that 50 Newton doesn't make any rotation with respect to the x, y, z. So that's 0 moment. And what about 100? The 100 one, does it do with respect to the y? No. Respect to the z? No, it's parallel. With respect to the x? It does. Yeah. Which one? The second one. Yeah. 50 Newton is has if the moment is tendency to rotate. If the system doesn't rotate, no tendency to rotate, no moment, right? So this is like you have a rotating disk, and you are pushing that in the center. It doesn't rotate. If the disk, you push it at a radius, it starts to rotate, clockwise or counterclockwise. But here, you are pushing a free object at its center of rotation. It doesn't rotate. So therefore, no tendency to rotation, no momentum. And with the 100, that would be only with respect to the x-axis. And let your 4 fingers of the right hand follow the 100 Newton, the direction of the rotation, and your thumb shows what? Allowing x or opposite x?
Like,
Well, opposite. Opposite.
all right.
Yes, that's 100 times the radius of rotation. What is the radius of rotation for that? 100 for the shortest distance. 3. Yes, that's 3. And the unit vector is I negative, because that's. And finally, with the 300, m of 300, Does this make rotation with respect to the y? No. Parallel with respect to the x? No, it collides with x. And what about z? It does. And what is the radius of rotation? 2 meters. 2 meters. And let your forefingers right hand follow the direction of the rotation. Your thumb, is this along z or opposite z? Opposite, yes. So that is 300, the radius of rotation is 2. And then that is opposite z, that's minus k. Everyone happy? No, no. All right, which part?
Sir, could you please explain with the example it along with x?
Yeah. Well, let me. I wish I had something to illustrate for you. So this is the plate, right? So this is the plate, okay? And that is x-axis, y-axis, z-axis.
Yeah.
Okay. Now, if I push here, and the only point which is fixed is here, that starts to rotate like that, right? So my four fingers follow the direction of rotation, and then my thumb shows down. This is positive z, that is negative z. So very same plane. If I push it like so, right, and this is fixed, it only rotates about which axis? This axis collide, that axis collide, and this one collides. Why? Because this force is free to bring here. That's like you have the force at the center. But if I push it like so, this is parallel to z, doesn't rotate. Collide with this axis, doesn't rotate about that. Only that would rotate like so, which is this axis, right? Thank you. All right, let's go to another. We have something more difficult. All right. So if you go, for example, to 3-4, okay, Serish, make sure you watch the yesterday's lecture. You missed the lecture yesterday. That was very important. All right, here we want to find out the rotation about an axis. Rotation about an axis is a scalar. So rotation by itself, moment is a vector. If you want to project it over an axis, what do? You do a dot product between the rotation vector and the unit vector of that axis. So in another term here, I have a unit vector of AA. So there is a unit vector for AA as an axis of rotation. So axis of rotation, you remember these doors have a hinge. So axis of rotation is that the door can rotate not about a point, but about a line. That line, we call this axis of rotation. Here, AA is like a hinge for a door. That's not a point, that's a line. The door is rotating about a line. Yes? Yes? All right. So here, F, two different things I want you to distinguish. If I say, what is the rotation about point O? Okay, that's a vector. It can rotate about X, Y, Z. It has three components. But if I ask you what is the rotation about the axis of rotation, that's not a vector. That's a scalar. And how do we find it? So first you have to find rotation of the system, and then pre-multiply that by the unit vector of that axis. So m is r times f. So r times f is rotation about a point, and then you want to project it about that axis. You have to pre-multiply that in a scalar by the unit vector of this one. So yes, for the sake of completeness, that is, we cover it, but I don't think that's very important for the exam. Don't panic. All three-dimensional things. I mean, eventually, this subject is to help you analyzing a structure. These are more fundamental things. If you want to study a complex three-dimensional structure, yes, you deal with them as a vector and then in a three-dimensional sense. But eventually, in these subjects, everything would be narrowed into two-dimensional bending of the beam and what forces developed inside the beam. That's a two-dimensional problem. So we cover this for the sake of completeness. So don't panic if you are not very just so f, no problem to write f. This is already been given in terms of the rotation. I need to make a vector between f and axis of rotation. The best vector is um, I go 4 units opposite x, 2 units along y, and another -1 along x. So 4 plus 1 is -5i, and then plus 2j. That's a position vector, plus 0k. That is r. This is a position vector which connects the vector to the axis of rotation. Any line connecting them could be used. That's the only line we have. And then the force components, we have it. And what is the unit vector of AA? So AA seems to be parallel to Z, okay? So the unit vector of AA, that is equal to K, isn't it? This is parallel to that is unit vector. So if I want to write this, first, the moment about that axis, you make a I, and here the first row you fill in with the R components, -5 to 0. The third row you fill it with the force component, 6 to 3. And then if you pre-multiply that by K, I mean, that, take it as a recipe. Uh, when you project a momentum with respect to an axis, that's what you get.
What we are calculating here?
Let me explain. This is UAX, UAY, UAZ, RX, RY, RZ, FX, FY, FZ. So just in the top row, if I want to calculate the momentum as a vector, I have ijk. But when I want to project it over a vector, that ijk, I take it away and put the unit vector of the force here. And then the outcome of this is not a vector. This is a scalar. So instead of ijk, I put the magnitude of direction cosines for that here. So if I go with that, this is for the axis of rotation 0, 0, 1, and for the position vector -5 to 0, and the force 6 to 3. That determinant, the outcome, is not a scalar. It is a scalar, it's not a momentum, because that's rotation about an axis. Rotation about an axis is not a vector. This is a recipe. I can prove it for you. When you pre-multiply a unit vector by another vector, you remember that we had this, if two vectors are dot product, that's ax bx plus ay by plus az bz. That's when you dot product two things. The very same thing happens here. You are pre-multiplying the unit vector of that axis with another vector, and if I want to write this, that's a convenient way of doing that. You construct a determinant. In that determinant, you fill the first row with the unit vector of that axis, the second row, the component of the position vector, the third one, the components of the force. So that is a very, I mean, what you take from this exercise, I want you to just think about the concept. Don't worry about the number crunching. The concept. What means if I have a force about a point? A force about a point can make a three-dimensional rotation. That three-dimensional rotation is a vector. We call this moment. Moment about a point. If I have a force and then I have a line, this force with respect to that line, what it produces is a rotation, but that rotation is not a vector. That rotation is a scalar. This is like I have a door. This is a door, right? This door can only rotate about this axis. It cannot rotate like this. It cannot rotate any other way. It can only rotate about an axis. So no matter how do I apply the force, it only can rotate like so. If I push it normal, if I push it at an angle, it only rotates like that. So that is rotation about an axis. This is a scalar, it's not a vector. But if I only hold this from here, one fixed point, and a force. So if I change the angle of the force, the rotation changes, right? So that's when you have a force and a point, the outcome would be a vector, a three-dimensional rotation. But when you have axis, pushing it, no matter how you push, it only can rotate about that one. The scalar vector.
Then how we calculate torque?
The torque is moment, the same. Torque, some textbooks they call it torque, that's moment. As long as the unit is force multiplied by length, Newton meter, that's torque, moment, the same. All right, let's go to page 125. All right, here in first example, that is a force with respect to a point. Is that a vector or moment, a scalar? C-14, a force, a point of rotation. This would result in three-dimensional rotation, right? So that's a vector. How do we find it? You have to define a position vector. Position vector is OB, and you have to write a force. The force is also provided as a vector. And let's go to, for example, 17. So a force about AB axis. Is this result in a scalar or a vector? That force compared to a line about the axis of rotation. Axis of rotation is AB. Is it a? It only can rotate about that line. It's not a three-dimensional rotation. That's only. This is a hinge. The brick would rotate about that axis. Can you imagine that? Yeah. All right. So how do we do it? I can do the number crunching or show you how this is done. But more importantly, I want you to get a insight. If I ask you this force with respect to the B, that makes a three-dimensional rotation. That's a vector. If I ask you the force with respect to the AB, that's not a vector. This is a pure rotation. That's a scalar. Okay, how do we find this one? Let me write down the formula for you. Um, so this is a good problem to get the concept. All right, so what do I need is unit vector of AB, unit vector of AB. I need that. And then I need the momentum, which is, momentum is, I have to connect from C to any point of that line. So it could be CB, it could be CA, it could be anything, right? So I need a position vector that position vector, I extend this one, and the position vector could be any point from this line of action to that vector, could be CA, could be CB, even it could be a point from here to there. But the only points we have coordinate for are A and B. So which one is easiest? Is it easier to describe AC or BC? Which one is easier? AC is easier, right? So AC, I take that as a position vector. So that is R multiplied by F. Okay? And then that is UXI, UY, J, UZK. So to find out, this is rotation about a point. How do I find rotation about the axis? Rotation about an axis, I have to pre-multiply UAB by that product. And how this is written, that is, you make a determinant. In the first row, you fill in three components of the U. UX, UY, UZ. These are for AB. These are for the axis of rotation. In the second row, you put the coordinate of R, RX, RY, RZ. In the last row, you fill in the component of the force. Fx, Fy, Fz. So apply to this case. Okay, we easily can find the unit vector of AB. You know how to find the unit vector. And what is the position vector? You suggested the position vector connecting the force to the axis of rotation to be AC. So that is AC. This is taken as AC, and AC is what? AC is 2K, right? And 2K is 0I plus 0J plus 2K. So when I want to fill here, I put 0, 0, 2. And when I want to fill in here, I put.
Sorry, can you just read this part again?
Sorry?
Where you wrote 0, 0, 2?
Which one?
How did you write 0, 0, 2? How did you do it again?
Okay, you want to go from A to C. What is the vector? You just go 2 meters along the K. That's 2K. 2K has 0I, 0J. So if you write that vector in a three-dimensional case, this is 0I, 0J, 2K. And then you fill here 0, 0, 2. Right? Okay, and finally, F, where are the components of the F? The components of F are 50, minus 40, 20. And what about the unit vector of AB? I can show you quickly the unit vector of AB. You want to go from A to B. You want to go from A to B. How do you go there? I personally go minus 4 along the X direction, followed by 3 meter along the Y. So in that journey, AB is minus 4I plus 3J plus 0K. Okay? And then the unit vector for that is 16, 9, 25, 5. All right? So then the unit vector for that is minus 4 over 5I plus 3 over 5J plus 0K. Right? Now I put these components here, minus 4 over 5, 3 over 5, 0. All right? Not a big deal. I mean, it looks very hairy and scary, but that's, once you understand the difference between force about a point, force about the axis. One is making three-dimensional rotation, the other one makes the scalar. How to calculate the scalar? Don't worry about the derivation. Exam is not about derivation. All you need is that formula. So you pre-multiply the unit vector of that rotation axis by the vector of rotation. So vector of rotation are R, X, Y, Z, Fx, Fy, Fz. And the first row, you only put that of the unit vector for the rotation of axis.
Could you go to the slide again?
Yeah, let me go there. Yeah. Why did you choose engineering? The other class, what subject they're having fun, listening to music, you are doing tough things. Okay. If you want to do something, let's see what else we can do. Well, the very same thing here. I mean, with that problem, can you tell me 200 with respect to the O? Is that a vector or is that a scalar? Vector. And 500 Newton with respect to the OA. Is this a vector or a scalar? Okay, good. 1 to 6. All right, so this is easier to visualize. I mean, that's a star question. It means that that's a super complex, but for you, that should be piece of cake. Hello, Natasha. Make sure you watch the recorded. Okay, let me summarize what you missed. Okay, so I want you to make a difference between two different concepts. One concept is you have a rigid body. This is a rigid body. And then with this rigid body, you can only fix a point, only a point, right? So it means it can rotate, it cannot translate. So if you want to push it in X direction, you can. If you want to push it Y, Z, it can rotate. It is only free to rotate. Rotate about the X, rotate about the Y, rotate about the Z.
But you can't move it.
Not translate. Translation, you cannot, because this prevents that from translation. But rotation, you can. Rotation about that point. So if this object is fixed at a point and you apply a load, it makes a three-dimensional rotation. It depends how I apply the force. If I change the direction of the force, the rotation would change. So that is the first concept. The first concept is you have a three-dimensional force, one fixed point. The outcome would be a moment. A moment is a three-dimensional rotation. All right? So that is the first concept. One point, a force, that's a vector, the three-dimensional. But now imagine this is a door. A door has a hinge, and this hinge is a line, it's not a point. So if I have this door, can you move the door like that? You can. This is fixed. The door is fixed. You only can rotate it like so. Yes? The door can only rotate like that. You can rotate the door like that, right? Because it's rotation about an axis, not rotation about a point. When you have rotation about a point, that is three-dimensional. When you have rotation about an axis, that's only one rotation. So the first one is a vector because it's three-dimensional. The second one, that is a scalar. It only can rotate about that axis. All right. So here we are talking about two different things. If you are being asked about a force with respect to point C, that is a vector. That is position vector cross product by F. But if I ask you what is the rotation of F with respect to the CD, CD is not a point, it's an axis, right? So with that axis, the outcome would be a scalar. That's a rotation about that axis. So this is what we discussed in the last, I don't know, 1 hour. So just make sure you go and watch that. So I just summarize that for you. All right, how do we do it? First of all, I need to have the unit vector of CD. Yeah, no problem to find unit vector of CD. The first thing is, and then I have to write F as a three-dimensional vector, but with F, yeah, okay. This one does not give me the magnitude of F. It tells me the outcome, the scalar final value should be 750 Newton meter. No problem. So, well, I can write F in this way. F is equal to magnitude of F multiplied by unit vector of AB, right? Correct? All right. And what about the position vector? The position vector is a vector which connects one point from the force to one point from the axis. So the easiest one is AC. AC is easy. So if I write AC, AC is what? 1.8.
Could you repeat the line again? Why we take it?
Sorry?
Could you repeat the line again? After AC?
Could be AD or AC. What did you say?
No, yeah, we are taking AC. Why we are taking AC? Short, that's all.
The shortest?
Yeah.
Which one is shortest?
No, I'm taking, why you are taking AC? That's all.
Because this is the axis of rotation, CD, and you have to choose one point from the axis of rotation, choose one point from the force, and connect them together. The easiest way is CD because it only has X component. I could have chosen DA. DA is a little bit more complex. That is, I think that's CA, not AC, CA, and that is 1.8 I plus 0J plus 0K.
Why did you shift?
Yeah, because the position vector is from the coordinate, from the point of rotation to the vector, not from the vector to the point of rotation. Okay, now if I calculate this, that's almost all I need. Let's try UCD. CD by itself is, I want to go from C to D. First, I travel 1.2, 1.2 is 2.4 J, and then um, travel 1.8 along K. Okay, that's 3. So the unit vector is 2.4 divided by 3J plus 1.8 divided by 3K. Easy. And what about, all right, the next one is unit vector of AB. So unit vector of AB, you want to go from A to B, I go minus 1.8 I, and then 2.4, sorry, 1.2 J, and finally 3.6 K, right? 3.6 K. This is not the unit vector. That is AB itself. That is that has to be divided by magnitude of AB. So magnitude of AB, what is magnitude of AB? Let me calculate. This is 4.2. So UAB is all right. And now I can write the force vector. So what would be the force vector? The force vector is magnitude of F multiplied by that unit vector. All right, now I think we can fill that determinant, the determinant which give me the rotation about the axis. That is rotation about, what was the axis called? That was a CD, was it? CD. Oh, we calculated, did we calculate CD? Yeah, we did CD. So rotation about CD, that is a 3 by 3 determinant.
You can do it both with CA as well, right?
You can do the dot product, you can do the determinant.
I can take CA instead of CD as well.
CB, no. That's rotation about CD. That's rotation about the CD. Yeah. The door hinge is CD. So its unit vectors you fill in the first row. That is 0, 2.4 by 3, 1.8 by 3. And then the second one should be the position vector. What was the position vector? The position vector was CA. That is 1.8 here, 0 here, 0 there. And what about the force component? The force component are the force component are, this is minus 1.8 F divided by 4.2, and the next one is 1.2 F divided by 4.2, and finally 3.6 F divided by 4.2. And then this is an easy determinant to calculate. And you have to equate that to what? You have to equate that to 750 Newton meter. And then by solving that, you find the magnitude of F. That's easy. So the left-hand side is a scalar, but it has an F in it. The right-hand side is a number. So you divide both sides by that. That gives you the F. So let me zoom out. You can copy the screen. Page 134. Okay, that is about a couple. You remember the couple? Couple is when you have two forces of equal magnitude, opposite direction. The forces are parallel. They only cause the system to rotate normal to the page which contains the forces. So example of that is being shown here. How many couples you find in the 3-19? How many couples you find here? I can pair these 300 and that 300, that give me one couple. Then I can pair 400, 400, that give me the second couple. And also I can pair 200 and 200, that give me another couple. So how do we combine all these together? So when you want to combine scalars, you use clockwise, counterclockwise. So the couple due to the 300, 300, that is clockwise. I write this as a negative number. The couple due to the 400, 400, that is counterclockwise, that is positive. And the couple due to the 200, 200, that is clockwise, that's negative. So once you add all three couples together, the outcome, if the outcome is negative, so the system would rotate clockwise. If the outcome is positive, the system would rotate counterclockwise. Yeah, clockwise is negative, counterclockwise is positive.
How can we know?
Yeah, yeah. How can you know? Good question. Let me explain. All right. So this is the beam.
Which one? Where is the?
I'm talking about 3-19.
Yeah.
Yeah. I'm talking. Let me write this down for you. Don't take in shortcut. All right. Um, Forty Chasal and um, Nguyen. 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 Yeah. So this is a frame. You want to put it on the wall. Okay. But you only have one pin. Put this pin anywhere you want. Any one. You just put that one, fix it to the wall with one point. And then if that frame is on the wall and is fixed with one pin, you apply 400. How does the frame rotate? So the pin is not on, yeah, it is anywhere. It rotates clockwise or counterclockwise. So just watch me.
If the pin has to be on the beam.
This is a frame. It's a family album. It has my grandfather on it. All right. I put it here, but I'm short of the pin. Only have one pin. I fix it to the wall, and then 400, 400, 400, 400 apply. Does it rotate like this or that? This way?
Yeah.
Counterclockwise. Okay. The very same frame, I have one pin. Pin it here, and then I apply 300, 300. Does it rotate like this or that? That is clockwise.
Yeah.
Clockwise. So the same frame here, one pin, 200, 200. Does it rotate like that or this? 200, 200. Does it rotate like this or that? Clockwise, negative. So now you understand? Yeah? I have very great respect for my grandfather. Yeah. All right. So let's watch the next one. Um, with this one. This one. How do I do this one? This is a bit tricky. I mean, very simple, but just a simple trick. All right. Well, in overall, the problem is very similar to the previous one. The only difference is if I want to calculate the couple requires the shortest distance between the forces. So how do I find the shortest distance? That might not be a little bit trigonometry if I want to do it this way. So I have to find the shortest distance is this one, right? Okay, if you are capable of calculating that one, that's easy. To find out the couple, that is 10 kilonewton multiplied by this shortest distance between the two forces, that's D. That's one way. And is this going to be clockwise or counterclockwise? Clockwise. But we want to do it in an easy way. So to do it in an easy way, any suggestion? How can I do this even easier? Can I break the forces into their components? What happens if I break the forces into components? That's what's going to happen. So 10 kilonewton projected horizontally, 10 kilonewton projected vertically, right? And then this force 10 kilonewton doesn't exist. If I project it here, 10 multiplied by 3 over 5, that's 6. And 10 projected over here, that is 10 multiplied by 4 divided by 5, that is 8. So I'm breaking that force into 8 and 6, one being vertical, one being horizontal. The very same thing I can do here. So I break that one into two forces, and this doesn't exist anymore. And now this is 6, that is 8. So how many couples are there? Two couples. One couple is a pair of 6 and 6. The second couple is a pair of 8 and 8. So the pair of 6 and 6 is counterclockwise, that's positive, and the distance between them is 2 meters. The shortest distance between them is the 2 meters. And the pair of 8 and 8, that is clockwise, and the shortest distance between that is 4 meters. So we just avoided doing the trigonometric calculation by breaking the forces into the components. You could have done it in a more sophisticated way.
How could the distance between 6 and 6 is 2 meters?
Between 6 and 6, good question. All right. So whenever you are not sure, just extend line of action, right? So I want to go from here to here. 1 meter, another 1 meter from here to there.
The vertical line.
Yeah, 2 meters. Question.
So could you explain
Uh,
the diagram?
the whole diagram. You want to explain it again?
Yes.
All right. So we did have two forces of equal size, opposite direction. So that is the classical definition of couple. A couple is when you have two forces, equal magnitude, parallel, opposite direction. And to find the magnitude of the couple, that would be 10 multiplied by shortest distance between 10 and 10. But finding the shortest distance between 10 and 10 is not easy. You have to do some trigonometry. So if you can do it, no problem. You get the answer, and the answer is going to be clockwise. But if you are lazy like me, you would break that forces into parallel to the dimension which are provided. What dimensions are provided? The dimension of 4 and 1 are provided. So I'm breaking that in parallel to the 1 meter, 4 meter. This is the XY coordinate. If I want to define an XY coordinate, that's how I define them. That's X, this is Y. Why did I choose that coordinate system? Because they're parallel to the dimensions which are provided. It is convenient. And then projecting these forces into components, that I hope everyone can do. It in this new scenario, I have, instead of one couple, I have two couples. No problem, the couples have to be combined together properly. How do I combine them? Making sure the sense of direction is being accounted for. So 8 and 8, they are making a negative clockwise direction. 6 and 6, they are making a positive counterclockwise direction. So,
I don't understand the direction part.
okay, just the very same thing. All right, let me explain this for you. I took a photo of this one, put it on this frame. This frame on a piece of the wall, and I have one pin, tag pin. The tag pin you can put it anywhere you want. Right, put it like that. And now I'm pushing this one and putting this one up, this one down, and this is fixed only at here. So this rotates like that or rotate like that. So is it clockwise or counterclockwise?
No.
So these two are going to be
So the 8
negative.
is
Yes,
clockwise, right?
that's clockwise.
That's where I got mistake. Maybe you said
Okay, my mistake. And 6 and 6, one in here, if you push it like that, does it rotate counterclockwise or clockwise? Anti-clockwise. Positive.
If you put one when you just on one.
They help. They only help to rotate in the same direction. Yes, they're helping. I mean, even if one is acting, that rotates. If the second one is acting, make it faster rotate. All right, going back to the problem sets. Now we jump into 135. So maybe we still can do something from 134.
What about the F23? F2, F323?
Give me the number.
F323.
23. Yeah, 23. Let's do it. That's a good choice. All right, here we've got three moments and we want to combine them together. All right, so how do we combine vectors? We just add them. But that has to be a Cartesian addition. So for every vector, you have to write them in ijk. It's easy to write MC2 in vector. How do we write MC2 in terms of vector? We started the easy one. MC2. How do I write it as a vector? The magnitude is 25 kilonewton meter. But what is the unit vector? Just use your right hand. Four fingers are following the direction of the rotation. Your thumb, does it show positive Z or negative Z? Negative Z. So that one, I have to write this as minus 25K. Any objection to that? Just let me to explain again. So your four fingers right hand, they are following the direction of the rotation, and your thumb, does it show positive Z or negative Z? Negative Z. And that's minus K, right? The unit vector for that is K. All right, so the trick is going to be with M1 and M3 because we have the magnitude, but the unit vector of that we have to construct. So how do I construct the unit vector of 1? Unit vector of 1, I'm trying to construct it. Unit vector of 1. That is a line, as I see it, that is inside the ZX plane. ZX plane, or no, maybe this is three-dimensional. So to go from here, there, right? So three components in it. So the components are, the Y component is like so, the X component is like so, and the Z component is like so. Happy? All right, let me write this down. I write the vector at the numerator and its magnitude at the denominator to make it a unit vector. So that is minus 2I plus 2j plus 3.5k, correct? So minus 2I plus 2j, 3.5k. Yes? All right. What about the magnitude? Let us work out the magnitude. 2 squared, 2 squared, another 2 squared, 3.5 squared. And then the root, 4.5. So the unit vector of 1 is minus 2 over 4.5 I plus 2 over 4.5 j plus 3.5 by 4.5 k. Yes? Or now we are able to write MC1 as a vector. MC1 as a vector is magnitude of MC1, which is 45, and that is positive U1. Positive U1, your forefinger shows the positive of U1. That multiplied by this unit vector.
So why multiply?
Sorry?
So why are you multiplying this?
I have to multiply that together, yeah. So yeah, 45, 4.5, that's 10, right? So that would become, I mean, that's easy to calculate. MC1, that is minus 20I plus 20J plus 35K, okay? So we do the same thing for the last vector. The last vector,
So you multiplied MC1 with the unit vector.
I multiply the magnitude, which is 45, by the unit vector, and 45 divided by 4.5 is 10. 10 multiplied by this term makes it minus 20, 20, 35.
But did we make from it?
What I get is the moment C1 as a vector. That's the magnitude of the vector multiplied by its unit vector. Okay, we do the same thing for 3. Anyone can help me with the unit vector of 3? What is the unit vector of 3? Unit vector of 3. That is, I have to go from here to there, right? So let me show you. That is positive 1.5 minus 2j, correct? So I write this as a fraction. That is 1.5 I minus 2j and divided by the magnitude of that hypotenuse. What is the magnitude? That is 1.5 squared plus 4 root. That's 2.5. 2.5. All right, so now we managed to find the unit vector of the third one. If that is multiplied by 30, which is the magnitude. So M3, the moment of the third one, that is its magnitude, 30, and multiplied by the unit vector. Multiplied by the unit vector. And what do we do last? We want to combine them. So three vectors, how do you combine them? Easy. Just add I components together, j components together, k components together. So um, I think we can do, these are good conceptual questions, this page. We can do as many, even 20, 21, 24, which one you want to do, and we can do all of them.
We didn't did 20 type of thing.
Which one?
20.
20, yeah, let's do 20. Okay, tell me how many coups are here?
3.
Three. And that is very straightforward. Very straightforward. So the first one, I mean, all of these are two-dimensional planar. We have to do this in a scalar way. And then the coups are coplanar. How do we add them? Is this counterclockwise or IJK? Counterclockwise is easy. So with the counterclockwise concept, the first component of the coup is m of 150. That is 150 multiplied by zero point 0.4, which is 60, right? 60 Newton meter. And if these are my x and y component, this is going to be clockwise or counterclockwise? Counterclockwise. That's positive. Yes. So 150, 150. There are two parallel forces, opposite force. That's the definition of the coup. A coup is when you have two parallel forces, equal magnitude, opposite direction. That is when you want to fasten a screw, you want to loosen a screw. You apply a coup. Okay? So that's a one-dimensional rotation. That's what you apply to the screwdriver. 150, 150. The tip of the screwdriver, when you rotate, one resists this way, the other one resists opposite way. So that's how much coup you apply to it. So that is due to the 150, 60 Newton meter, and that is in the counterclockwise direction. That's positive. Or if I want to stick to the IJK definition with this coordinate system, that rotation is this positive I or negative I?
Positive.
Positive I. Positive K, positive K. So that is positive K, because just this is X, Y, and XY, does the positive Z project out of the paper or inside the paper? XY. If this is my XY direction, the positive Z, is this coming out of the plane or inside the plane? Don't, yeah, right hand rule. X to Y. X to Y, that's the positive Z, out of the plane, right? If you go from X to Y, that's, look, this is always true. This is always true if you have a coordinate system with three axes, x, y. How do you know the third one positive? So use your right one from the number one, which is x, go to the number two, which is y. Your thumb shows positive three, which is z. So that is positive z. Positive z. The very same thing here. Just go from x to y with your right hand. Your thumb shows positive z. And the next one is the couple of 300. The couple of the 300. That is 300. What is the distance between them? 0.4. That is 120. 120 Newton meter. And is this positive K or negative K? 300, that comes out of the plane. That is positive K again. And the last one, M of 200. Okay, that is 200 times 0.4 is 80 Newton meter. And again, positive K. Okay, all you have to do is add three numbers together. That's
Excuse me, sir. I'm so confused. How we do it?
yeah. Okay, right hand. Right hand, you hold it like this. So this is the thumb, this is forefinger. Just you bend it like that, okay, toward yourself. And then let your four fingers follow the direction of the rotation. Direction of the rotation is from x to y in the counterclockwise, okay? And then your thumb shows the third dimension, which is z. So this is called the right hand rule. So here, for every coup which we calculated, so you know the direction of the rotation, let your forefinger do the rotation, and your thumb shows the direction of the, whether this is projecting out or projecting in. If that is rotating like this, it's projecting out. If that's rotating like that, it's projecting in.
Can you give an example?
Example of here? Okay, let's take example of 300. 300. That is, I hold my hand like this, right hand, and the rotation is that way, correct? For 300, the rotation is like that. So I rotate my finger, four fingers, the thumb is coming out of the plane.
You mean which 300, the right one or
I'm talking about both of them. The couple is both of them. They are helping each other to make the rotation, not one of them. That's the concept of the couple. The couple is two forces at the same time helping to the, when you are doing a steering wheel, you don't do it with one hand, you do it with two hands, right? So one hand is pulling up, the other hand pulling down, it makes a rotation like in couple. So with couple, always there are two forces involved in opposite direction, equal magnitude. Whether you are working with a screwdriver, there are two forces. Whether you are working with a steering wheel, whether you are working with a, I don't know, tool or something.
why are we only writing with respect to the z direction? Like, why are we having our all the forces in the written down in k?
K.
K.
Because we define x, y. These are planar forces. All forces are sitting in the same plane. So how do you choose your coordinate system? You choose x and y to sit on that plane, the plane that forces are acting, and coup or moment is always perpendicular. You remember that from energy and motion. If forces are acting in one plane, the rotation is out of the plane or inside the plane. that is very similar to the
So
XYZ.
whenever we get a situation like this where something is inside a plane and the plane is not mentioned, we automatically assume that the XY plane and then the hoop will be acting opposite
Out of the plane or inside the plane. Yeah.
on the wheel. Yes.
Okay. Choice of coordinate system is up to you, but when you are dealing with the coplanar forces, all forces are on the same plane. So you know that this is either normal to the plane out, normal to the plane in. No other options. All right, so we go to the next one. Sorry, yeah, let me zoom out. And here you add all three of them together, that's 260 Newton altogether. The total moment, that is 260 Newton meter.
It's going upward, right?
Yeah. All right, we do that for 21 also. All right, how many coups are here?
Two.
Two coups. And you want the result of that to be 1.5 kilonewton meter. So what should be the magnitude of F such that the total coup is 1.5? So what we do is we find them one by one, add them together, set that equal to 1.5, and that gives you an equation. By solving that equation, you find the magnitude of F. So starting with the rotation of, and then here again, let me take my coordinate system like X and Y. Starting with the rotation of 2 kilonewton. That is 2 multiplied by zero point 0.3. That is zero point 0.6 kilonewton meter. And is this plus K or minus K?
Plus.
Plus K.
Plus.
Plus K. Everyone agrees that that's plus K. And what about the coups of F? Coups of F, that is F multiplied by zero point 0.9. And is this positive K or negative K? Negative K. Okay? And 1.5 clockwise. Is this 1.5 K or 1.5 minus K?
Why is minus?
Because with the F, if you rotate like that, that is inside the plane. So outside the plane is positive K, inside the plane is negative K. Yes? Or so with that answer, the final outcome, that is 1.5 positive K. And the unit is kilonewton meter. So both sides of the equation, the units should be the same. So here I have 0.6 plus or minus 9F over 10. That is equal to 1.5. So if I take 1.5 to the other side of the equation, that is 0.9. So that 0.9 is equal to 0.9 F. So F is equal to 1 kilonewton.
Can you please explain like the direction of K for the people?
All right. So in the three-dimensional sense, there are always three coordinate system. Okay? We call this 1, 2, 3, or we call this X, Y, Z. All right? So you can look at this from the top. If you look at top, you only see X and Y direction. Okay? And then you might ask yourself, okay, which one is positive Z? Is this coming out of the plane or is this going? If you look it like that, you don't make a mistake. Try to do the right hand rule. So this is 1, 2, 3 or X, Y, Z. X, Y, Z. If you go from X to Y, Y to Z, Z to X. That's in a clockwise direction. So X, Y give you Z, Z, X give you Y. So in either of these two planes, you can apply right hand rule. So what is positive X? I go from Y to Z, my thumb shows positive X. If I go from X to Y, my thumb shows Z. If I go from Z to X, from Z to X, my thumb shows positive Y. So look at this diagram here. Look at this rotation. So this rotation tells you either of two planes that give you the third plane positive. So when you are looking at the top, generally speaking, in this problem, you only go from X to Y. So from X to Y, that's the direction of rotation, right? So use your right hand, go from X to Y, that is Z coming out of the plane. So here, you don't have any problem to visualize, but when you're looking from the top, that could be a little bit tricky. From top, just use your right hand. That is called right hand rule. Right hand rule. So with your right hand, bend your forefingers, let your forefingers to rotate, and your thumb shows positive. If you rotate it this way, your thumb shows inside the plane. And inside the plane, compared to that positive Z, that's negative Z.
Like with the diagram from the picture.
From this picture, the positive Z is counterclockwise. If you go clockwise from that picture, that is opposite to Z.
Uh, with that one, I think
1.5 is taken from the total moment should be 1.5 kilonewton meter clockwise. And clockwise is negative. Clockwise is negative. Yes, so that is minus. If that's minus, yes, you take this that way. This is.
but the result is
Sorry?
the result is one.
No,
If it's positive, it's minus one.
if this is minus 1.5,
Yes, so you roll 0.6 over here and then minus x.
that makes 2 point. Yeah, that changes the answer, doesn't it?
Yeah.
So this is minus 1.5 minus 6, that is minus 2.1 equal to zero point 0.9 f. So f is minus 21 divided by 9. So that is 7 t. Minus 7 over t.
If you throw minus 9 to minus 9 over 10 to the other side, it's going to be
Well, mf is negative also. Yes, yes, that's negative also.
so,
Yeah, yeah, yeah. This is negative. That is negative. And then negative, negative, you get positive. All right. Let's go with the last one.
The first week is only one assignment.
Sorry.
Or two, right? The first week, the assignment is only one.
The previous problem,
Yeah.
there were two cooks.
No, no, I mean like assignment from last week. Just only one time.
We had one introduction. The introduction was
Yeah,
to.
because when I look at it, it's like two introduction words. I looked about the same problem.
This is a problem with Pearson. Every time, only one of them you have to do. If that's repeated, only do one of them.
But sir, now it shows that I never attempted. Because like the one is due on 6, the one is due yesterday. But when I look at it, it's all the same.
If they are the same, you only do it once. Yeah.
I've done it, but it shows that you never. It's not.
Don't worry. Don't. I fix it for you. I manually override this. Don't worry. These are Pearson is an external tool. That's not on Canvas. That's external. Sometimes these things happen. All right. Okay. Whenever you're ready, just let me know. I wonder why you never come to the consultation. If anyone needs help, yesterday I was sitting there 10:30 to 12:30 for consultation in a student hub. Just feel free to come and see me. That's your time. If you want to use it, just come there and see me.
What's the consultation time?
That is Tuesdays, 12:30 to sorry, that's 10:30 to 12:30. A student hub.
during the
Um, Send me email and well, that's the other time. My times are full. Yesterday I did 7 hours of talking, and your class is good. The other class I have, the first year student, they are few students who just make it hell for me. I went home like this. Just when I woke up, I was still shaking. So you're a good student. You're a good student, but in a different way.
10 to 12:30. We only free from 12 to 2.
Yeah, we have
On
taken
Tuesday and
as
Wednesday.
well.
Most of them.
Well, just email me if you have question. Email me. I try to help you. Or you can record a video if you have problems. I'm recording all these videos. They are being uploaded on YouTube because YouTube is easier than Canvas. Canvas, yesterday I lost my way to BA building, and then I tried on my mobile. It came like that, lots of text. No matter how much I zoomed, I couldn't get the room number. Suddenly a student saw me go, oh, there's a class is over there. I never could find it on my mobile. So YouTube, you can do it anywhere. On train, it streams, and even if your bandwidth is not great, you still can watch it little by little. But Canvas, maybe you cannot rotate it. You have to go to the Collaborate Ultra, find that things, find the right date. So apart from the YouTube, I have the solution for all these questions. If you want some extra question, just ask me. I see if I can send you the solution. I cannot post them on the web. These are copyright material. I cannot post them on the web. But individual inquiries, if you just are interested to see the solution for a problem, ask me. I try to get the solution emailed to you individually, not publicly. So we can upload the canvas, right? We can. Then these are copyright material. But individual inquiries, hopefully, no one put me in jail for that. All right. So this problem, I am only interested to know how do we do it. Anyone can tell me in terms of steps, one, two, three. Here we have definitely one coupe, but the problem is with that coupe, I know the magnitude, I know the shortest distance, and if I want to tell you the magnitude of the coupe, no problem. The magnitude of coupe is what? 450 multiplied by 4 over 10.4. That's the magnitude. But if I want to write it as a vector with ijk, I don't know the unit vector of the plane normal to 450 plane. If you pass a plane through the 450, that's not a flat plane. That's a plane at an angle. Can you visualize that? Yes, it was working with angle like x and z angle. X and z axis is the angle with the. Well, I mean, yes, you can do the shortcut, but generally speaking, um, we can do this in a vector way. In a vector way. So, or other alternative is I can break 450 into two components along the ZY plane, and yeah, I can break that into two components in ZY plane. And that makes the problem two couples. Then the couple should be added together. The first couple is in the k direction, the second couple is in the j direction. So you know that your rotation only has two components of the k and j. You want me to do it in detail or yes? All right, let's do this in detail. So if I resolve 450 to two components, 450 multiplied by 4 over 5, that's 360. 360 is the horizontal one. And the vertical one is 450 multiplied by 3 over 5. That is 270. All right, so this is 270. That is, sorry, this is 360. And this one is 270. So this force doesn't exist anymore. We resolve that into two components. Now I have two moments to calculate. The first moment is moment of 270. So what is the moment of 270? That is 270 multiplied by zero point 0.4. That's 108. And 108, is this positive K or negative K? Sorry, I'm talking about 270. That is 270 is J. This is 270 is J, right? Is this positive J or negative J? Positive J. And what about the hoop of 360? 360 multiplied by zero point 0.4 again. That is 144.
So the 360 is perpendicular to Z, right? Is that right?
The 340, if you pass a plane through 360, that the plane is in the Z direction. But with that direction, you get a positive K. But that one
Positive K, yes.
is a positive K, yeah. Okay, so finally you have to add these two components. The total rotation, that is minus, it is plus 108J plus 114K and 0J, 0I. That is the total rotation.
Can you explain what is positive J again?
Positive J. Okay, positive J, that is 270, 270. So does this rotate this way, right? So I take my hand.
How do you know rotate that?
Sorry?
How do you know rotate that?
Look at the tip of the arrows. The tip of the arrows. The tip of arrows shows you the direction. So you are looking into the ZX plane. ZX plane is rotating like that. And if you rotate, your thumb would be parallel to Y, positive Y.
It's clockwise, is it?
That would be counterclockwise. If you look at that plane, 270 makes a counterclockwise rotation.
And why J direction?
Because that's parallel to the y-axis. Y, the unit vector for y is j. This is you're rotating this way.
It's not according to
Yeah, 270, 270, they are sitting in which plane? They are sitting into the zx plane, right? So that has to be normal to the zx plane. Normal to zx plane is y. Is either plus y or minus y. It's plus because the rotation direction is counterclockwise.
Okay. So for the small triangle, so which angle should we look at to get the
Okay, a small
right?
triangle. A small triangle. With that small triangle, I redraw it here. That is 5, 4. That is 3, 4, 5, right? Yeah. Now, you want to project 450 over horizontal. That is 450 multiplied by sine of this angle, cos of this angle. Cos of this angle is 4 over 5. Okay, if you want to project this vertically, 450, that is horizontal. If you want to project it vertical, 450 should be multiplied by 3 over 5. That is sine of this angle. Or you can do the similar triangle. Similar triangle, 450 is hypotenuse, 5 is hypotenuse. 4 is the adjacent term, the x component is adjacent term. 3 is the vertical one, 3 is the opposite side. So you can do a similar triangle between the forces and the triangle. That similar triangle, if you solve that, shows you how you project that. All right, I think that that's enough for today. Let me do the attendance.
If I has value, so the path of also stick with the y. If I has value.
I have value.
Yeah.
What do you mean I have value? Yeah, yeah. I doesn't have value. Yeah. In this case, that means. Uh, Let me explain that to you. This rotation cannot be about the y-axis. This is like you are. This is like you have an axis which is perpendicular to the plane of two forces, and your system can only make a rotation like the door does. The door cannot do a three-dimensional rotation; it only rotates about an axis. So in this sense, uh, the axis of rotation, the hinge, is normal to the plane that holds 450 together. Can you pass a plane through the 450? Can you visualize you're passing a plane through 450? So that would be like this. So if I pass a plane through 450, that plane looks like this one. So this is a plane I pass through the 450, and the moment is going to be normal to that. Okay, normal to that is like the axis of the hinge, and now this plane can only rotate in that plane. It doesn't do a three-dimensional rotation. It only rotates normal to this plane. That's why it doesn't have a zero I. Yeah. All right. So just bear me a second. I complete the attendance, and then you are free to go, and or just ask question. Okay, Sehrish is here, Natasha is here, Nguyen here, Chaisal here, Daniel away, Abdullah here, Jonathan away, Ahmed away, Nijil here, Barnaby away, Flynn away, Shah here, Darcy away, Porty here, and For some reason, I have to do it again. So this time we have
Teacher, sir, can you pronounce my electronic teacher name? Sir.
Said.
Yeah.
Said.
We call him Say.
Just to tell you, Said is under a very difficult issue. I cannot tell you what. Just be very considerate with him. He is going through a most difficult thing now you can imagine. Yeah, just give it to yourself, but just be mindful of that.
Thank you.
Bye. Have a good day.
Thank you. Thank you. Thank you.
See you,
See you.
sir.
See you. Don't worry about anything. You are doing absolutely fine. Don't worry about a thing.
Thank you, sir.
Thank you.
Have a good day.
You too. You too.